This is John Black, Superchemist. I'm going to go into what an electron configuration is. Okay, electron configuration is basically a set of numbers and letters that tell you the number of shells with electrons, the shape or type of orbitals, and the number of electrons in each orbital. And keep in mind, all these facts and these electron configurations, they're just for individual atoms and not for when two atoms combine. When more than one atom is involved, orbitals will hybridize. Okay, and I'll get into that in a later video. Now, before I start going into the electron configuration, I want to just give you a double check on this. You can see shell 1 has one s orbital. Shell 2 has an s orbital and a p orbital. Shell 3 has an s orbital and a p orbital. And then we'll start going into the freaky stuff. So all we have is an s orbital, an s and a p, an s and a p. And then we're all the way up to the 4s and the 3d. So if you started hydrogen, you'd have 1s1. The reason why is because you have first shell, it's an s orbital, and it's one electron. Now helium would have two electrons. They'd go into the same s orbital, so it'd be 1s2. First shell, type of orbital, how many electrons? Now remember, when you go to the second shell, you always start out with an s orbital all the time, every time. So you're going to start out with your same 1s2 because you still have these electrons, right? Then you're going to move into 2s1. That'd be 3 electrons. And that's what lithium has, 3 electrons. Now beryllium has 4 electrons. You still have to fill out your s orbital and have 2 in there. So you'd have your original 1s2, 2s2. A boron, remember, you jump over to the p orbitals. You're still going to have everything that the last person had. 1s2, 1s2, 2s2, 2s2. But now you're going to have a p orbital that you're going to put 1 into. And it's in your second shell. So it's a 2p1. You do that the same to carbon. You have everything the same. 1s2, 1s2, 2s2, 2s2. But you're going to add another electron to your p orbiter. So that's 2p2. And you do that all the way down to neon, where you'd have 6 electrons into your p orbital, right? Now, you could, if you wanted to, like for boron, you could see everything's the same except for this p thing here. You can actually name your p orbitals. 2px1, then you would have 2px1, 2py1, because remember, you're putting them into each orbital first, the x1, the y1, the z1. Then you can start putting the second one in. But that's just a little FYI. So now you're down to your third shell, right? Now you can start, this 1s2 stands for helium. See how they're the same? We could have just replaced 1s2 with He, just like we did here. The last one we did was neon. So all of these numbers are the same, except for you're adding one more electron. So you can actually put neon. Neon, and it's the third, 1, 2, 3, the third row down, meaning the third shell, s orbital, and there's 1 electron, 3s1. Next one is magnesium. Just continue on. You had neon. You're putting another electron into the same s orbital. So it's neon, 3s2. Now remember, there was 3d orbitals there, but they moved them down a row, so because you don't put them in yet until you get to the 4th shell. Until you have all your s orbitals and p orbitals filled up in the 3rd shell, then you can go and start worrying about d orbitals. So you'd skip magnesium, you'd skip the 3d orbitals, and you go to the 3p orbitals. Neon, 3s2, just like over there, 3p1. You do all that up to argon. You keep just raising this number up, 2, 3, 4, 5, until you get up to argon, which is 6. Now that's where things get weird, right? you got potassium, which argon's the last thing you did. It had filled up the entire orbital in that shell. So you have argon 4s1, because you always start out with an s orbital, right? Calcium, easy enough. Argon plus 4s2. Now I went over scandium in the last video about how when it fills in its orbitals, when it's at a +3 state, that it would actually fill in the d orbital, the 3d orbital, before the 4s2 orbitals. And that's true. But in this case, it doesn't matter which ones get filled in because we're just doing an electron configuration. So it's argon 4s2 3d1. And you just continue down titanium. You're just adding, just like up here, you add 1, 2, 3, 4, 5 until you got to 6. You're just adding until you get up to 10, right? Titanium is 2, vanadium is 3. Now this is the first one that gets weird, how I said that they start adding in different ways, okay? As you can see, a d orbital has 5 orbitals, but you can fill in 2 into each one of them, right? And you want to fill them in individually. You have to have all 5 filled in with 1 electron before you can start adding a second electron to an orbital, a d orbital. Now I want you to think of, why did this happen? Why did they take one of the s orbital electrons and put them into the d orbital? Why would they do that? The reason why is, if you think about it, if they did that, you either have all your Ds, this way they have all their Ds filled up with 1 electron, and their 4s's only has half. Or you could do it the way they kept doing it, and you'd have your 4s filled up completely, and you'd have your 3d having 4 electrons. 1 electron in every lobe except for 1. It's just lower energy for this atom to have 1 electron in every d orbital, 1 electron in the s orbital. Okay, you need to take physics. That's beyond this video, but you have to take my word for it that that's the way it goes. And there are 20 other elements, d block elements, that do freaky stuff. I'm just trying to give you an example of why this does this. It's because this way it gets to fill up. It only has half of each orbital filled, but they're all half filled. All the D's have 1 electron, all the S's have 1 electron on these orbitals I'm showing you. And that's just, it's lower energy that way. Now as for this, why do these, like I was saying, if you take 3 electrons away from this, it will fill up this 3D one and leave this empty, right? Why would it do that and not do it over here, okay? Why doesn't it fill in its D? This should be argon 3D1. If it fills in the D's first, then it should fill in the D's first over here. But it doesn't do that, and the reason why, every time you add a proton on, you also usually add a neutron on. You make this bigger. And you would think, well, so what? You add a little bit on there, you might. But if you look at, say, this is calcium and this is scandium. Now I want you to be aware that these two things here, I just messed up. This should be moved over more. This has nothing to do with this. These are two separate atoms, okay? It's just that I should have moved that over and erased it, but I didn't. But keep in mind, this is one thing, and this over here is a different, separate thing. It's just, I ran out of space there. Say this is calcium and this is scandium. These two right here. These two right here. The difference between the nucleus size may only be a little bit, but the field that generates the shell is a lot bigger. And you can see the difference between this and this, even though you only have a little bit of space here, that's different. Look at this cube here. I couldn't even draw a cube because it's so small. But look at this cube. The area and the volume is just drastically changed, meaning there's more spaces for the d electrons to go in between the p orbitals. Okay, when it's this small, it doesn't happen because there's not enough room. The repulsion between the other electrons is too high. But once it gets this size,
This is like the line. Once it crosses this line to scandium, it's big enough to let the d orbitals be filled now. Okay.
Always remember, science is great.